Okay, perfect. So thank you everyone for being here today. So today we'll talk about specific debugging functions in Windows that has been presented by Alex Ionescu a few years ago. So today it's not about the discovering of these debugging functions, but more like how we can weaponize it to include it in malware development. So for starter, my name is Yoann. I'm a security auditor at Waystone, a French company, and I'm mainly performing some red team operation, and I'm doing a lot of research and development on malware and how we can inject Cobalt Strike or any command and control beacon to ease this kind of operation. I've performed some talk on malware development at Le Hack in France, at Insomniac, and some malware development workshop at DEFCON 31 and 32. So start with an introduction about Nirvana hooking. So the Nirvana hooking is specific debugging functions that has been implemented in Windows and allow to execute a code every time a specific syscall is triggered. So if you take the standard path, you have a process, for example, notepad.exe, that is trying to access the kernel with a syscall. The syscall is processed by NTOS kernel, and once the kernel has performed the action, it will send back the systhread to notepad.exe and give back the execution flow to the process. The Nirvana hook will be placed between the kernel and Notepad. So Notepad will still send a syscall to the kernel will perform the syscall, but before sending back the execution flow to the process, it will send the systhread to the Nirvana hook that has been registered. The Nirvana hook will process the systhreads and send back additional information and send back the execution flow to the notepad.exe. So this is quite interesting for debugging purpose, because you can just track any syscall that has been performed by the process. You can manage action when a specific syscall is performed, and you can just monitor how the process is working. So this is the intended purpose of the Nirvana hook. So how is it working internally? It just when the Nirvana hook is registered, the kernel, before sending back the execution flow to the process, the kernel will just look at if any Nirvana hook has been registered, and will just jump to the Nirvana hook address. So when we are creating a new Nirvana hook, we have to handle the execution, and we have to prepare the hook functions to ensure that we redirect the execution flow to the userland function that has been called, that has performed the syscall. So we can do this with a small assembly code. So we're just preparing the stack with a push RBP. We are saving some interesting parameters. So for example, the register AAX that will contain the systhread. We are saving all this data, and we will then call the Nirvana hook. Once we have called our interesting functions, we can just restore the stack, restore all parameter, all register, and send back the systhread to the calling functions, and jump to the register R10 that contains the calling function address. So this is a 10 line of code that allow you to execute arbitrary code in a specific process. So, as I said, the kernel will jump to an arbitrary address that has been registered in a process. Usually, there is some protection that are called control flow guard that avoids the jump to untrusted address. These protections are usually implemented on userland, so as it's a kernel that will perform the jump, we can see it as a specific control flow guard bypass. The problem is that if we decompile the kernel, we can see that protection has been re-implemented on the kernel level. So it's just the function validate user call target that's allowed to do a secure jump and check if any control flow guard rules has been implemented. So Nirvana hook is not a control flow guard bypass. It's just a way to execute specific code in a process. So the question now, now we know how we can create a Nirvana hook, is how we can register a Nirvana hook in a process. This can be done using a specific function, an undocumented function stored in NTDL, which is called NT-set information process. This function is used for several purposes, and one of its purpose is to create, to register a Nirvana hook. So as you can see in the code, the last step we call NT-set information process. Yeah, here. And we are giving some, the process we are targeting, a specific value that say we are, trying to add a specific Nirvana hook, and the address of the Nirvana hook we are trying to add. So this address here is just the address of the assembly code, that is, presented here. So once you have called this address, these functions, the Nirvana hook has been registered in the process, and every time the process will perform a syscall, the specific code that is created here, instrumentation hook, will be called. So that's it. It's a few lines of code to create, to register your Nirvana hook. So this is nice for debugging, but we are trying to weaponize it. And the first thing that comes to my mind is intercepting syscall result. It can be interesting to intercept syscall results because we are able to change it, and if we are able to change it, we can affect the execution flow of a program. For example, if your program is trying to create additional memory with virtual alloc, for example, you are able to see that a new allocation is asked by the process, and you can change the syscall to say that this memory has not been created and reuse it by yourself. So this is a way to force the creation of additional memory space in the process without running specific code. So to perform the systhread hijack, we have to keep in mind that the kernel performs a jump and not a call to the hook. So all the parameters that are given to the kernel will be given as is to the Nirvana hook, and the systhread will be stored in the RAX register. So all we have to do is we just have to change the way, the value of this register before giving back the execution flow to our process. So this is how we can modify the Nirvana hook at the end. Instead of restoring the RAX value with the previously saved systhread, we can just set the result of our Nirvana hook implementation. And by this, we will just change the systhread, and we will be able to modify how the process will see the execution succeed or not. So this is for the the assembly code in the Nirvana hook. We can look at the C implementation of the Nirvana hook implementation. So this is the function that will target a specific syscall, specific functions, and will change the result. So for this, we have to implement something. The first thing is to detect what is the syscall that has been asked by the process. So this can be done using the dbg-help DLL functions that, given the specific address, can retrieve the symbol associated with this address. So for example, if you give the address specific address, it will say how this address is related to virtual alloc, or this address is related to create remote thread. So this allows us to target a specific function, a specific NT function. The next thing is an anti-recursive variable, because when you will call function in a Nirvana hook. If this function is called another syscall, you will go into a loop and you will just loop into your Nirvana hook, and it's something we don't want. So we just create an anti-recurse variable that is set to 0 at the beginning, set to 1 when we are entering the Nirvana hook, and reset to 0 once we are out of the Nirvana hook. This avoids the loop in the syscall. And that's it. At the end, we can just return the value we want. And due to the fact that RIX, the register will be just give back to the process, the return value of Nirvana hook implementation will be the new systhread. So if you set 0 on the Nirvana hook implementation result, all the syscall you will be performed will be known as successful. If you set another value, it will be an error. So, yeah, so this is, for example, the code we will be running. So this code will just create two sections with NT-allocate virtual memory. The first one without the Nirvana hook, the second one with a Nirvana hook, and we will see if there is any difference. So, yeah, let's go for the demo. Yeah, that's it. Okay. So, as you can see here, our first interlocate virtual memory call has been successful because we didn't tamper anything. But the next one, we have created a Nirvana hook that sets the systhread to C5, and this is known as an error code. So for the process, it's look like the allocation didn't succeed. But if we look at the memory of the process, we will see the new section created. Because the kernel created the section, it's just the process that didn't know the call succeed. So that's what I said before. With this kind of hijack, you can make a process believe that its a memory allocation didn't succeed, and you can just hijack the new created section to inject your malicious payload. So for example, if you see a process creating a read, write, execute section, you can just set the systhread to a failure and reuse this section in order to set your malware without needing to create a section in your process. So this is kind of interesting, but it's hard to use in a real life because usually when a systhread failed, the program can crash if you don't handle well how it's if the process did not handle well the failure of a given syscall. So yeah, it's interesting, but not really production ready. So we can go further and look at another way to weaponize the Nirvana hook, and this is more interesting. It's about process injection. Process injection is a malware development technique that allows to inject a malicious code in a legit process. It is really interesting because it allows you to hide a process, a malicious process, into a legit process. So it's something we are trying to do when we get an initial access to a workstation, to a user, or to any machine. It allows you, for example, to fully hide your command and control beacon from detection by a human or EDR. So when we are trying to do process injection, there is three steps we are trying to do. We are trying to allocate memory, write memory, and execute what we have written in the memory. Usually, what is complicated is to compile a process to execute an arbitrary code. With the Nirvana hook, we have a way to compile a process to execute arbitrary code on a regular basis. And if we look at the NTSet process information function that is used to create, to register a new Nirvana hook, we can see that it can be used to target a remote process. If you look here, Yeah, if you look here, you have the hproc parameter, which is just an handle to a process. So if you set this handle to another process, you will set your Nirvana hook to the remote process. So this is kind of interesting, and you can use it to just create a Nirvana hook to a remote process without needing to write additional code in it. The problem is that if we reverse the NT-set information process, we will look that it's limited to administrator users because you need the SA debug privilege. So this is not process injection you will do as an initial access, but it's more post-exploitation technique. Once you have fully compromised the machine, you can set your persistence with a process injection using this Nirvana hook. So how you can do this? It's just you target your process, for example, notepad.exe. You will allocate a memory inside this process in order to write your Nirvana hook function, your Nirvana hook code. You will modify the Nirvana shell code in order to call your Cobalt Strike beacon that you will also have to write in your process. You will use the NT-set process information in order to register a Nirvana hook and trigger the execution of your Cobalt Strike beacon. So there is some problem here. The main one is that you will need to have a RWX, so read, write, execute buffer in your notepad.exe function. This is something that can be fixed with some time and research. This is needed here for debugging purpose, but that's something that can be fixed. So, yeah. So the Nirvana hook needs to be modified because previously we had a Nirvana hook that has been used only to follow the syscall execution and hijack some systhread. And now we are trying to do something more interesting. We are trying to create a new execution flow inside the process. And for that, the code is not really complicated. You will just save all your context. You will call your Cobalt Strike beacon, whose address has been written in the RAX register, and you will just, at the end of the execution, reset all your context in order to give back the execution flow to the process without making it crash. So there is a problem here with the shellcode with the assembly on the left, is that every time a syscall will be performed, your Cobalt Strike beacon will be executed. So you can just have to add an anti-recurse features. It's just you add a new instruction that will overwrite the first instruction on the Nirvana hook. So this is an instruction here. This instruction will just, when executed, will remove the push RBP and replace it by a jump R10. And the jump R10 will directly give back the execution flow to your calling process. So the first time the Nirvana hook will be called, it will execute your Cobalt Strike beacon. But the second one, it will just jump to R10 and give back the execution flow, and nothing will happen. So with this, you can be sure that your beacon will be executed only once and not every time a syscall is performed. So we can try a demo on this. So I will just compile my beacon up. We run our notepad.exe, and yeah. So as I said, you have to be in an administrator session, and you can just set process injections. You're waiting. That's okay. It's cold. You're looking that your notepad is well working, and you should have in your Cobalt Strike, yeah. Yep. In your Cobalt Strike, you have your new beacon executed in notepad.exe, and this beacon is fully working. And you didn't have to create a new thread in the process did it by itself, and your beacon is working. So if we look here, what happened is that we are opening our process, we are deploying the hook in the process, so we have just created a new section, or we are using some misalignment in the byte to find an empty space, a code cave. We are writing our hook directly in the process memory. We are writing our Cobalt Strike beacon also in the process. And then we are deploying our Nirvana hook using the NTSet process information. And all of this allow a smooth injection of Cobalt Strike beacon into a notepad.exe, even under EDR detection. So I find it quite interesting. I don't know if I have a slide. Yeah, I don't have a slide about it. But there are some problem with this, is that the NTSet process information is a function that is known by EDR. So if you reverse this function under EDR, you will see that some userland hook has been implemented directly in NTSet process information. So I've done it only on Sentinel-1. And hook is created, but it didn't raise any alert. So I think it's more informational than for preventing process injection. But yeah, as every technique of malware development is not bulletproof, it's something that will work for a few months, and after EDR will just implement the detection for this use case. Okay. I don't know what time is it. Okay. So process injection is really interesting. Being able to perform a process injection without needing to call well-known Win32 API such as create remote thread is really interesting because it's allowed to bypass a lot of EDR solutions. But when you are using command and control, there is another use case you have to keep in mind is that your beacon will sleep. And a lot of EDR solutions focused on the state of the beacon to detect it. For example, if you are using Cobalt Strike without any obfuscation, during the sleep of the beacon, you will have a specific set of bytes in memory, and EDR solution have a specific pattern to detect this memory pattern. And while your beacon will not be detected when injected or when performing action, it will be detected when it sleeps, it goes to sleep, or come back from sleep. So sleep obfuscation is the second important part when you are using process injection with the command and control. There is a lot of sleep obfuscation techniques. The most known one use what we call the APC callback on waitable timer. So it just creates before going to sleep a timer, and when the timer expired, it will execute a specific code that will awake the beacon, encrypt all its memory, and allow him to perform its specific task. If you are using, for example, only the sleep function, because on your beacon you can just call your sleep 60 seconds and wait for the beacon to awake. If you are using your sleep, you will see on your stack that your beacon is using the sleep function, and a lot of EDR solution will detect also this kind of pattern of thread stacks pattern. So to avoid this, there are some techniques such as the thread stack spoofing that allow you to modify the stack of your beacon when it sleeps and make it look like a standard thread in the process. For example, if you are targeting a Chrome process, you can mimic the thread stack of a real Chrome thread when your beacon is asleep, and it's allow you to bypass some detection. But these techniques are known, and a lot of EDR are starting to detect it. So, for example, the APC waitable timer is used by the Echo or Nighthawk sleep obfuscation, and a lot of solutions exist to detect specifically this technique. If you're using thread stack spoofing, it's only targeted to a specific process. So when you compile your beacon, you will be able to only inject it on a specific process, because otherwise your stack will not match the injected process stack. So yeah, some technique exists. The one with Nirvana hook I will be presented. I find it really interesting because the whole game in sleep obfuscation is to be able to awake your beacon. So it's to be able to program the execution of arbitrary code at a specific event. So that's why APC callback on waitable timer are used, or just a sleep function that's wake back by itself. But with Nirvana hook, we have a nice primitive that allow you to execute arbitrary code every time a syscall is performed. So, yeah. So, what we can do with Nirvana hook, and that it's complicated to do with other sleep obfuscation, is we can just erase all our beacon from the memory. When you are using sleep obfuscation, usually your beacon still reside in memory, still reside in the stack, in the thread stack, sorry, and if it exists, it can be detected. So the idea here is not to make the beacon sleep, but just to kill the thread. If you are killing the thread, and if you are removing every IOC from your beacon from memory, it will be harder for the EDR solution to detect it. So the idea is just you kill the thread when you want your beacon to sleep. So in fact, it's not sleeping, it's just dead. You save its context, so the register, the stack, the heap, everything. And when you want to perform an action, you just use a Nirvana hook to trigger the respawn of the process. So by respawning, we said just create a new thread, modify its context, and rerun all the code related to your beacon. So with this technique, when the beacon is sleeping, in fact, the beacon doesn't exist in the memory. So if it doesn't exist, it's harder to detect. The real goal here is to be able to reset the thread context, and for that we have a nice function that is called anti-continue, that can be used to resume a thread execution with a given context. So for example, if a thread, if an exception happened in your thread, you can use anti-continue to just reset the thread context and rerun the thread with a specific context, avoiding your program to crash. So when we will make our beacon spawn, we will just use anti-continue to reset all the thread context to make it execute your beacon. So how we can do all this? So the first thing, as I said, is to save the thread context. So this can be done quite easily with the RTL capture thread context. So before killing your thread, you just call these functions, you capture all your thread context, and you save it somewhere, so on the stack or on the heap. So this is the easy part. The next things we have to save is the beacon stack, because in the beacon stack you will have all the information that has been collected by your beacon, every information needed to perform connection with the command and control, and it's something you want to keep to avoid creating new session every time the beacon awake. So you save the stack by just getting RSP and getting the beginning of your stack beacon. You make the difference between this and you save all the data stored. So when you start your beacon, you will just save somewhere the initial stack address, and when you are trying to sleep, you will save somewhere the current stack address, and you will save all the data contained between these two addresses. So yeah, quite easy. After saving all this context, you can just kill your thread. The beacon will stop existing, but you have to restore the rewake the thread and restore the context. And this is the hard part. So to awake your thread, you can use a Nirvana hook. The Nirvana hook will be triggered every time a syscall is performed. So the Nirvana hook will be configured to just create a new thread and trying to restore the context. By restoring the context, the first step will be to restore the stack. And this must be done carefully because if you just copy your stack at your given stack address, the functions that is trying to awake the beacon will start erasing your backup stack every time it's creating a new variable. So, for example, at the left, you will see that your thread is starting. You have your awake functions that is used to restore the context and rerun your beacon. And you have just copied your backup stack right after the awake function stack. The problem is that when the awake stack will grow, it will start erasing your backup stack. And you won't be able to recover this data and your beacon will crash. So what you have to do is just you start your thread and you will copy your backup stack between the thread start stack address and the awake stack address. This allows the awake function stack to grow without deleting any data. So after this, you have successfully copied all your backup stack in memory. But the problem is that if you have any pointer stored in the stack, pointing on other stack information, you will have an offset between the old stack address and the new stack address. So you have to relocate every pointer stored in the stack. This can be done easily by just parsing all the stack, so all this data, and trying to see if the information stored pointed on the previous stack information. And if you see any address like that, you just add your offset on this address, and it will be pointing now on the new backup stack address. So with this, you have been able to fully restore the stack. So once your beacon will start running again, it will find all its data and it will be able to communicate with the command and control without crashing or without creating new session. The next step is to restore the thread. So restoring the thread context is easier because you can just modify the different register. You can modify the stack address. You can modify the pointer. The two main information you have to modify is the RSP pointer to make it point to your new backup stack address here. And you have to modify the REP pointer to make it point to the next address after the sleep in the beacon. If you just modify it to point on the initial address of your beacon, you will just restart the execution of your beacon from 0, and you will lost all your information. Once you have modified all this context, you can just call the ntContinue function. And as I said before, the ntContinue function will allow you to re-inject all this thread context inside your beacon thread. And now you have everything you need to respawn your beacon. And to respawn your beacon, you will use a Nirvana hook to schedule your thread respawn. You will use a Nirvana hook. So before killing the thread, you have saved all this context, and you have created a Nirvana hook that will call the awake function. This Nirvana hook will be called every time a syscall is performed. So if you just let it like this, every 1 or 2 nanoseconds, your beacon will go back from sleep, and it's not something you want. So you have to modify your Nirvana hook in order to be executed only at a specific time. And this can be done by just saving into the heap or the stack the time you want the beacon to be respawn, and in the Nirvana hook you just compute the difference in time, and if this difference of time is more than the sleep time configured, the Nirvana hook will be executed and will respawn the beacon. Otherwise, it just gives back the execution flow to the process without any problem. So yeah, so this works, but it's not really stable due to some limitation of Nirvana hook. It's something that can be fixed with time, but we can try to make a demo with this. So for this, I have custom command and control server. So nice. I'm sorry, I thought I have prepared this before. Okay. So here is the command and control. It's really look like Cobalt Strike because I used the UI of Cobalt Strike as inspiration. And yeah, we will just compile our beacon with the simple, so it's not an OPSEC injection, it's just as a demo. Yeah. And yeah, we'll have okay. Okay, so you have your beacon here. It looks like running, and you see that the beacon is sleeping and going back from sleep every 7 seconds. We can look here at the thread stack. And as you can see, you didn't see any thread related to the beacon. It's all thread related to the process. And if you look like this, anytime the beacon go back from sleep, you don't see anything. So you don't see anything because process hacker doesn't catch it really well. So we can just kill the sleep mode up, and you will start seeing the beacon thread up. It will take some time. Please work. Okay, so this is the beacon thread. And you can see you have a lot of things related to it. It's coming from a specific address. So this is a beacon thread. And if you start up, if you kill the sleep, and you reset a sleep of 5, you will see that the beacon the thread just die and doesn't reappear before being slept again. So with this, you have a sleep obfuscation that prevents any way the beacon being alive in memory while sleeping. So the problem is that the method is not the sleep can make the beacon crash, can make something like that. It's not production ready, but it's a proof of concept that you can just kill a beacon and retime its execution before. Yeah. So I had some information on memory management that I don't have time. So yeah, if you have any question.
Thanks a lot, Yoann. Yes, time was flying and we're over. We maybe will take just one or two very short questions before the break, and then you can still discuss with him during the break. Any question in the room? There is one here in front. Oh.
Nice presentation, thank you. You say there is nothing in memory when you kill the thread, but where do you store the data for the stack and so on for the beacon?
Yeah, I lied. Yeah, it's more you don't have anything executable in memory. The only thing you have in memory is just the part in executable memory is a part of the code used to respawn your beacon, but everything else can be stored in the heap, fully encrypted. So you can use a specific encryption to avoid detection, but you will not find any strings related to your beacon except a small part of the code used to awake your beacon. So yes, you have some IOC in memory, but it's less than just keeping your beacon alive in a thread.
Okay, thank